Welcome to lesson 2 of 4 in this tutorial, Changes in Energy. In our last tutorial, we covered energy stores and systems, looking at definitions and also examples of different systems. This time, we'll be focusing specifically on energy changes. In this session, we'll again be covering various learning objectives. We'll start off by looking at kinetic energy, move on to elastic potential energy and gravitational potential energy, and finally we'll cover the conversion between kinetic energy and gravitational potential energy. Again, here are the specification points for this session. We'll go through them individually, but it's a good idea to have a quick read through them before we begin. Let's look at energy changes in moving objects first. In this tutorial, we'll go through several types of energy changes. Firstly, we'll look at the kinetic energy of a moving object. We'll then look at the elastic potential energy of a stretched spring. And finally, we'll look at the gravitational potential energy of a raised object. Don't worry if you thought that was a little quick. We'll be covering each of these examples in the next section, starting off with kinetic energy. Moving objects will all have some form of kinetic energy. Kinetic energy will depend both on the object's speed, but also on the object's mass. If two objects have the same speed, then the heavier object is going to have more kinetic energy. If the two objects had the same mass, then the faster moving object would have more kinetic energy. This is shown here. This is a very important fact to remember, as it confuses a lot of students. You'll need to remember the definition of kinetic energy for AQA exams, as this is quite a commonly asked question. We can define it as the energy which a body possesses by virtue of being in motion. We can also define it using this equation. This equation is a very common one, and we'll look at how to use it very soon. When using this equation in an exam, it's acceptable to use the shortened form too, but just make sure you know what it stands for. The most important thing to note here are the units. The mass has been given to us in kilograms, whilst the speed is in meters per second. Most importantly, the kinetic energy that we're working out has to be in joules. This is important because a lot of AQA exams may give you the answer in kilojoules and you might have to convert it back. It's vital that you remember it's not just the speed that affects an object's kinetic energy, it's the mass of the object as well. This means that a fast-moving object may not necessarily have more kinetic energy than a slow-moving object, especially if the fast-moving object is much lighter. This makes sense if we consider this example. It takes lots more energy for a person to push a car very slowly than to push a light shopping trolley very fast. We're now going to apply this equation to an exam question. Take a minute to pause the video now and attempt it, then we'll go through it step by step. Okay, so our first step will be to look at the kinetic energy equation. As we've just seen in this section, this will be KE equals a half mv squared. Our next step is to put the numbers into this equation. In this question, we know that the kinetic energy is going to equal a half times the mass, which will be 500, times the speed squared, which would be 5 squared. We can simplify this further by working out that it equals 1/2 times 500 times 25. This is equal to 6,250 joules. Finally, we need to look at the units that are given in the question. Although ordinarily we would leave our kinetic energy in joules, this exam question has specifically asked us for the kinetic energy in kilojoules. This means we need to convert our 6,250 joules into kilojoules, which would be 6.25 kilojoules. We've now completed the first two specification points in this section, so we'll move on to the next one. This concerns the concept of elastic potential energy. When we stretch an object, it will gain elastic potential energy. This is shown in the stretched spring. When a spring is stretched, the kinetic energy of the spring is going to be transferred into elastic potential energy. Again, like kinetic energy, it's really important that you know the definition of elastic potential energy. This is shown by the energy stored as a result of applying a force to deform an elastic object. We can also define elastic potential energy using an equation, as shown here. You'll notice that it's a very similar format to the equation for kinetic energy, so it's important that you don't get mixed up between the two. The short version of the equation is shown here. Again, it's acceptable to use this in an exam, but make sure you know what each symbol stands for. The units for elastic potential energy are shown here. We've met the units for extension in meters and elastic potential energy in joules before, but the new one is the spring constant, which is measured in newtons per meter. There is an important condition to remember when using this equation. We need to remember that the limit of proportionality should not be exceeded. If it is exceeded, the spring will display plastic behaviour. This plastic behaviour would not fit the formula, and we would be unable to calculate a value for elastic potential energy. This is shown again here. Now let's apply this to an exam question. Callum stretches a spring which has a spring constant of 75 newtons per metre. He manages to stretch it from 40 centimetres to 60 centimetres. Calculate the elastic potential energy that is now stored in the spring in joules. Pause the video now and attempt this question if you can. This is the answer to the question. We'll work through it step by step, like we did in the first one. As always, we need to write out our formula first. This time, the formula we're using is the one for elastic potential energy. We met this a few slides ago. So it equals 1/2 KE squared. Before we can calculate anything else, we need to find the extension of the spring. In this question, we need to watch out for our units, since extension should be measured in metres. If you look carefully, in the question, we've been given the units in centimetres, so I'm going to convert these from 40 centimetres into 0.4 metres and 60 centimetres into 0.6 metres. This means I can now calculate my extension in metres, which is simply 0.6 minus 0.4 to give me 0.2 metres as the extension. Now that we have a value for the extension, we can simply put our numbers into the equation. We also need to remember to give our units along with the final answer. So we'll take our first equation, which is EE equals 1/2 Substitute in the number for K, which is 75, and then also substitute in our extension, which we've just worked out as 0.2. This is going to give us a value of 1.5 joules. Lots of questions in AQA exams will make you change the subject of a formula. In this case, you could be asked to find the spring constant instead of the elastic potential energy, in which case you'd have to make K the subject. Now that we've finished the first 3 bullet points, we're going to cover the last spec point for this tutorial, looking at gravitational potential energy. As shown here, gravity is the force that attracts objects towards the centre of the Earth. To overcome the force of gravity and lift an object up, we must do work. As shown here, this requires energy. The energy used in doing work has been transferred from kinetic or chemical energy into gravitational potential energy. This means that the GPE gained in doing this is equivalent to the work done in lifting the object. Similar to kinetic energy, GPE is determined by several things. It can be determined by the object's height and also by the object's mass. We can demonstrate GPE through this diagram. On the floor, the brick has no gravitational potential energy, but once the boy lifts it up, the brick has gained in gravitational potential energy. We can define gravitational potential energy as follows. It is the energy stored in an object positioned at a height above or below the surface of the Earth. We can calculate the amount of gravitational potential energy an object has gained using the following formula. As shown before, this is going to involve mass, gravitational field strength, and also the height. This is the shorter version of the formula, which will be accepted in AQA exams. However, you must know what the symbols stand for. The units for this formula are quite straightforward. The only new unit we haven't seen before is the one for gravitational field strength, which is newtons per kilogram. Don't worry about learning the exact value for gravitational field strength in an exam. You'll be given the value for Earth in the question, or in the data sheet at the front of the exam paper. Let's try a practice question to consolidate our knowledge on this section. Joe weighs 70 kilograms. He climbs up a tree that's 12 metres tall. Calculate his GPE in kilojoules, giving your answer to 1 decimal place. Take the value of G as 9.8 newtons per kilogram. Now, you can pause the video and have a go through the question before we work through it step by step. The answer to this question is 8.2 kilojoules. Let's see how it works out. Our first step is to write out the formula for GPE. As we've just seen, this would be GPE equals mgh. Now we can put in the numbers from the question. This will be GPE equals our mass, which is 70, times our gravitational field strength, times our height, which is 12 metres. This works out to 8,232 joules. Since the exam question has asked for our answer in kilojoules, we need to convert from joules into kilojoules. This means we need to go from 8,232 joules into 8.232 kilojoules. However, we need to take note that our answer should be given to 1 decimal place. This means that our final answer would be 8.2 kilojoules. Now we'll tackle a slightly different scenario. A 72 kilogram diver jumps from 20 metres to ground level. What is the loss in GPE that he experiences? Assume that G is 10 newtons per kilogram and that the effects of friction and air resistance are negligible. Pause the video now to attempt this question. The loss in GPE experienced by the diver would be 14,400 joules. We'll work through the calculation step by step to see how we reach the answer. Firstly, we need to write out our formula for GPE. This would be GPE equals mgh, as we've seen previously. Now we can substitute in the numbers for our question. In this question, we know that we're looking at the loss in GPE, but we can write in that GPE is equal to our mass times 10, which is our gravitational field strength, times our distance raised. In this scenario, we know that the mass of the diver is 72. The gravitational field strength is 10. Our distance raised in this scenario is actually the distance fallen by the diver, which in this case would be minus 20, since he is going downwards instead of up. This works out to a value of minus 14400 joules. Now for the third part of the question. We need to deduce the loss in GPE that is being asked for. In this instance, we've already worked out the number that we need to write. However, that was a negative number since we are assuming that going upwards would be positive and downwards would be negative. Since the question is only asking us for the loss in GPE, we can simply write the number 14400 as a positive value. Using this question for GPE, we know that as the mass and height of an object increase, the GPE will also increase. This means that the mass and height are directly proportional to GPE. A skydiver will have GPE since he is high above the ground. A car will have kinetic energy since it's the energy due to motion. In this scenario, we're going to look at the stages of a skydive and explain the changes between GPE and KE at each stage. In the first stage, the driver is going to have the maximum GPE before his jump. He's at his highest point possible, so the GPE will be 100 and the KE will be 0. At the second stage, some of the skydiver's GPE will be converted into kinetic energy. This is because he is losing height above the ground. As he begins to fall, the GPE will also fall and he will gain velocity, so the kinetic energy is going to increase. Any GPE that the skydiver is losing will be converted into kinetic energy. In the third stage, the skydiver continues to fall and more gravitational potential energy is converted into kinetic energy. Stage 4 is very important, since this is the stage where GPE is at its lowest value and kinetic energy is at its highest value. This occurs just before the skydiver hits the ground. In stage 5, we have assumed that all the GPE has become kinetic energy. The energy can be lost due to friction and air resistance in the forms of heat and sound. Here's a quick 5-step summary of what we've just covered. First, the skydiver has maximum GPE before his jump. Then, as he jumps and accelerates through the air, his gravitational potential energy is going to be converted into kinetic energy. He'll continue to fall through the air, with more gravitational potential energy being converted into kinetic energy, until he reaches just above the ground, where he has minimum GPE and maximum kinetic energy. Finally, he'll hit the ground and the GPE will become 0, as will the KE. Now we'll apply our knowledge to this exam question. Peter has climbed 3 metres up his ladder to put boxes into his attic. He drops a box of old books, of mass 10 kilograms, from the top of the ladder, and they fall to hit the ground below. The books initially fell with a velocity of 20 metres per second. What is the kinetic energy of the books just before they hit the ground? Assume that the gravitational field strength is 10 newtons per kilogram, and the effects of friction and air resistance are negligible. See if you can have a go before we work through the answer step by step. The kinetic energy of the books just before they hit the ground is 300 joules. Let's see how we got to this number. Firstly, we need to work out GPE. This is the same formula that we've been using throughout this section, which is GPE is equal to mgh. In this question, we can ignore the velocity, as it's totally unnecessary. It's just there to put you off, but don't fall into this trap. Now we can work out the GPE of the box at its highest point. Previously in this section, we've mentioned that when an object falls from height, all their GPE is converted into kinetic energy. This can be applied here, since we've said in the question that the effects of friction and air resistance are negligible. We can therefore use our equation for GPE to find that it's equal to 300 joules. This GPE value will be equal to the kinetic energy. Our next question is a little more challenging, as it is worth 3 marks. 2 cars are driving up a mountain. Car A travels up to flag A at height 30 metres, whilst car B travels up to flag B at height 50 metres. Both hills have a 1 in 5 slope, hence the cars ascend 1 metre for every 5 metres travelled along the road. Assuming that both the cars have a mass of 50 kilograms and travel at 20 metres a second, work out the difference in the distance travelled by each car, the difference in the gravitational potential energy at the flag points, and the difference in kinetic energy. Take the value for G as 10 newtons per kilogram. That was a lot of information, but the question is asking us to choose the answer options given in the table below. Pause the video now to see if you can work out the correct answer. D is the correct answer. We'll work through each part of the question step by step. Firstly, we need to know the difference in kinetic energy. We can actually rewrite the formula, as I'm about to show here. Since we've got 2 cars, we can say that the kinetic energy is going to be equal to a half times the mass times the velocity of car A squared, which is VA, minus the velocity of car B squared. Before proceeding with the calculation, we can notice that the mass and velocity of the cars is the same. This tells us that our difference in kinetic energy is going to be 0. Now, we can work out the distance travelled by each of the cars. For car A, the distance travelled would be 30 times 5, which gives 150, whilst for car B, the distance would be 50 times 5, which gives us 250. To work out the difference, we'll simply subtract A from B to give us a distance of 100 metres. Now we can work out the difference in GPE at maximum using the formula GPE equals mgh. We can substitute in the numbers now. So in this section, A would be equal to 10 times 50 times 30, giving us 15000, and B would be 10 times 50 times 50, which is equal to 25000. This gives us a difference of 10,000 joules. This means that the correct answer to the question is D, since this is the only line that has a difference in the distance travelled as 100 and the difference in GPE is 10,000. The difference in kinetic energy we worked out at first, which is 0 joules. We've now covered all the specification points in this section, which means that we've reached the end of this tutorial. If you're unsure about any of the points listed above, feel free to skip back to the section and watch the explanations again. We've now finished Lesson 2.